Sushi roulette. So there's a game show, there's a wheel with 12 sections, 3 of which are wasabi bombs. Now, wasabi bomb is that green stuff that you put on sushi, and it's super hot. Now, it looks like they have to spin this wheel until they get a wasabi bomb. That's how they win. The question is, what is the probability that it takes 3 or more spins? Now, because they're spinning until they get a wasabi bomb, that's a geometric probability. So we still check bins just like before. So it is binary because either you get a wasabi bomb or you don't. It's independent because each spin has nothing to do with the spin before. Now the number is different because we're just going to say, well, what's the probability that it takes 3 times before we win? And that's okay. And then the probability of success is the same as 1/4. 3 out of 12 is the same thing as 1/4. And that's the same for each spin. Okay, now check this out. If we wanted to know exactly 3 spins, the probability that x is equal to 3 would be, well, 1/4 winning means 3/4 not winning. And if we spun it 3 times, we won on the 3rd try, and the first 2 tries were no good. So that's how you would figure that out. But this question is not saying that. It's saying 3 or more spins. So what we're going to do is, instead of 3, let's do 2 or less, and then subtract it from 1. So, in other words, the probability that x, okay, our random variable, is bigger than or equal to 3 or more spins, that's going to be the same as 1 minus the probability that x is less than or equal to 2. So what we would do is we'd say 1 minus geometric CDF. Okay, so kind of like normal CDF. It's that number and less. What does that give us? So you can plug it in the calculator just like that. So let's see what I get. And the answer is 0.5625. So there's an over 50% chance that it would take 3 or more tries before you got that wasabi bomb. Okay, let's do the last one. Okay, let's see. Prisoner of war. John Carrick tossed a coin 10,000 times and got 5,067 heads. If the coin is perfectly balanced, the probability of a head is 0.5. Okay? Find the mean and standard deviation of the number of heads in 10,000 tosses, assuming that the coin is perfectly balanced. So this is a binomial situation. So we should probably start with bins. And so bins. It's either heads or it's tails. Each coin flip has nothing to do with any other coin flip. They are independent. The number is set. He's going to toss the coin 10,000 times, and the probability is the same for each toss at 0.5. So what is the mean and standard deviation? So the mean would be, well, the mean of this random variable is going to be 10,000, the number of tosses, times the probability, which is 0.5. So we should expect to get pretty close to 5,000 heads or 5,000 tails, however you want to look at it. Standard deviation. So the standard deviation, so give or take how much, that's going to be 10,000, I can tell I'm going to run out of room already, times 0.5 and 0.5, right? Your probability and 1 minus your probability and square root of that whole thing. So standard deviation is 50. So give or take 50 coin flips. Okay, so make that look like an A. How about B? Explain. What are we explaining? Oh, could we use the normal approximation? Well, yes, because if we take the probability and we multiply it by the average. Wait, what is it again? Hold on a second. No, it's the probability times the number of tosses, right? N times P. Get it right. So we should get 5,000. And then we do the opposite, which is 1 minus P, the probability, which actually gives us the same thing, times 10,000. And that's also 5,000. What do these numbers... Wait, what do we do with these numbers again? They just have to be bigger than 10. They are way bigger than 10. So our normal approximation for this thing is going to be fine. Which indicates when they start to talk about normal approximation, I'm thinking z-score is going to be coming up. Okay, let's see. So yes, they ask us in letter C the probability of him getting right here 5,067 heads. Okay, so of course he could go the other way. So because of that number in either direction, but let's just do the z-score. Here we go. The z-score, right, is the number that we got, 5,067, minus our average, which is 5,000, divided by the standard deviation, which is 50. And we want to say, what's the probability that we get that many or more, actually? So it shouldn't be equal to, it should be like that. Okay, so what do we do? Normal CDF. Okay, here we go. Normal CDF, and we want to make sure that it's bigger than this number, so we're going to subtract it from 1. Okay. So we get 1.34. 1.34. And normal CDF, subtract that from 1, and I'll see what we get. So the answer is 0.09. So 0.09. Okay. So here we are. This is 5,067 or more, right? So that tells us 0.09 right there. So that is for that. But we do have to consider the other way, because if we got 4,933 would be 67 in the other direction, which would also say, well, what if we have less than that? So, in other words, we have to add, here, we're here, and here. So what's the probability that we get more than that many heads or less than 67 heads? More than 67 heads, less than 67 heads, and then we add those two together. So the answer should be 0.18 altogether. So what does that tell us? Well, there's an 18% chance that this would happen if it was a balanced coin. So 18, that seems pretty high. I think that this coin is balanced. There you go. Having fun with statistics while you're in a prisoner of war camp. Yay!